Hi, this is ET370, and today we're going to talk about diodes. This is going to be a two-part lecture, and in this first part, we're going to talk about diodes, an intro, their symbol, the fluid analogy for a diode, look at an actual diode and an LED. We'll introduce the I versus V curve, and that'll be used in what we will call load line analysis. It sounds scary, but it's actually not too bad. And finish it off with an example. And in the second part of this first lecture, we'll look at how a diode works, and we'll look at the p-n junction, and hopefully it'll be something interesting if you've never, heard about, or you may have heard about silicon and semiconductors, but if you never really figured out how that works, hopefully the second part of this lecture will be interesting for you. Okay, let's begin. So diodes, what are they useful for? Well, one big use in diodes, and especially for power electronics, is rectifiers and converting from AC to DC. So you have single phase AC that's oscillating and you want to have something that's DC, smooth with a capacitor. Diodes are going to be very useful. Or three phase coming in, those three balanced three phase or even unbalanced three phase, and you want to again convert it DC, diodes are very useful. They're nice because they have no moving parts. They're made of semiconductor material, and they're very simple. So two-pronged elements. So let's look at what they consist of. So it's a two-terminal semiconductor device that allows current to flow in one direction, right? So the symbol is just this. It's an arrow, okay? So we have an arrow, or a little triangle here with a little bar. And the part with the bar, the way I like to remember it is this bar is what we have as, we call it the cathode, which has the negative part. And the other side is the anode. And it's important, just like all elements, to when you analyze it, you want to put the current direction and the voltage polarity. Now, for a diode, you actually want to be very specific. You don't want to just be willy-nilly about it. You actually want to be very specific, and that is putting the minus sign matching the bar so that your voltage has this minus plus, just like the plus and minus for the anode and cathode. You also want your reference current direction for the diode in the same direction as this arrow. So it should be very simple to remember how to set up the specific current and voltage polarity and reference direction. Okay, so the direction matters, polarity matters. Just match the minuses, match the positives, okay? All right, there's a few mnemonics to remember this. Acid, anode current into device, so this is the anode current, or CCD, cathode current departs, so the cathode current leaves. That's saying the same thing, right? Okay. All right, so what's a simple fluid analogy? We have fluid analogies for charge, which is like water, for resistors, like a rusty pipe. Okay, well, for a diode, it's a one-way check valve, right? So imagine you have your anode here on this side, you have a little hinge, and you can see that if there's pressure that builds up on this side, the current can flow, right? So it can only flow in one direction. If a pressure were to build up on the bottom side, it would get stopped by this edge here, right? So very simple, okay? What does a real diode or LED look like? And a diode and LED behave the same way, except an LED emits light. So here is an actual diode. And let me turn on my light here. So hopefully there we go. Okay. So you can see here, there's a little band. I know it's not perfectly in focus, but there's a little silver band on the right. But that's it, two-pronged device sitting like this. So you can see that this is the cathode right here. That's what that band represents. So pretty simple. That band is like the minus sign, the cathode. What about an LED? Well, this is behaving like a diode. This only allows current to run in one direction, but this time when current runs through it, it actually lights up, which is cool. So this is a light emitting diode, right? And the way it's constructed is you have this round part. And if you look very closely on one side, it's hard to see on the camera, but one side is flat. And I can see this, and one side is actually flat. I don't know if you guys can see it on the camera. Let's see if we can get in there. I'm gonna try. Hit the focus button. Let's see here. Is that, whoops, no, that's the rotate button. Let's see here, focus. Yeah, that's going to be difficult to see. Sorry about that. But I think the idea is clear that the cathode side is going to be flat. And that's actually an easier way to see it is that you have the shorter lead. This you guys can see. There's the shorter lead right there on the right. Okay, so the shorter lead. The anode is the longer lead, right? And so this is the side, if you want to have this light up, you want to put the positive voltage on the anode side. Okay, now inside you have these two pieces of metal here, and inside you have the reflector cup and some silicon going on, and then it actually emits light. I believe we got a Nobel Prize for discovering this. Pretty cool, because LEDs have allowed us to really make efficient use of energy and provide light at a much cheaper, both cost-wise and energy-wise way, okay? All right, let's look at this current versus voltage curve, okay? And so we have our LED, right, or diode. We have current going in, voltage, and notice that we have the minus matching. We have the arrow matching, great. And we have two simple states, basically on or off, right? Basically, if the voltage here is negative, we're going to have a blocked condition. Current's not going to be able to go in. So if VD is negative, blocked. If VD is positive, we will have current flow. And so let's say we put this in a simple circuit right here, right? Here we have voltage where the positive polarity is down here at the cathode. No currents can flow. The check valve is blocking. And here you have current flowing, okay? This is what we call reverse bias, and this is what we call forward bias, all right? And what if we were to plot voltage versus current, these two values, voltage versus current, what we would see is on the left half plane here, when the voltage is negative, we have reverse bias, current is zero, right? This whole thing is reverse bias. And on the right side here, we have forward bias. And now notice something, this is like a non-linear effect of the diode. You need a little bit of voltage here before you start pulling current through this guy. So you might even go back to this hydro analogy and think, well, what does that mean? Maybe there's a little spring load, right? There's a little stiction here or something. Something needs to be overcome on this positive pressure for it to allow current. So even if you had like 0.01 volts, you might not draw current. But once you break that forward voltage, maybe between something typically between 0.7 and 2.5 volts, then you'll see current. And now I exaggerated this line here. Usually it's very steep. It's very steep, okay? And here it's zero or nearly zero, and then it folds up. And then we call this the knee of the curve, right? Okay. Now, this concept called load line analysis is actually more general than just this diodes, right? You can use it for other situations. But in this sense, it allows us to compute the current and voltage of a diode when placed in a circuit. Okay, and so we look at this curve and you're like, well, okay, you have this, but where does it operate, right? Well, it depends on the external circuitry. It depends on the voltage that you're applying to it, right? If you increase the voltage, you can see you would be at a different point. So how do you know where you operate? Well, that depends on the circuitry. So let's look at a slightly more complicated example where we now have a resistor here in the path, okay? We still have the ID and VD. We still have it all set up in the same way where the current arrow is in the same direction, the negative and the negative match, right? But let's just see what happens, right? So what we're going to do is we're going to combine our ET250 analysis, right? So this is last semester's course. And we're going to combine that with this guy here. So what do we have going on? We have the resistor here, and we can use our good friend Ohm's law, or more specifically nodal Ohm's law, to actually compute the current, right? So how would that work? We have a resistor, we have a current, in this case ID, going through it, and we go ID equals the voltage, the node voltage at the one end of the current, which in this case is Vs, and here we have the ground, minus the node voltage at the head of the arrow, which is VD, so Vs minus VD over R. Perfect. So hopefully that's a good review. Okay. Notice I can break this out actually. I'm not doing anything magical here. I'm just saying, okay, minus VD over R is this guy, Vs over R is this guy. So this looks like a Y equals MX plus B kind of situation with a negative slope. Okay, so something that looks like that. All right. Okay, let's keep going. So what does that look like? Well, it looks like this. So we have the nonlinear curve, the IV curve of the diode itself, and we have this line plotted on the same figure, right? So this here is going to be Vs, and this here is your y-intercept Vs over R, right? Where they intersect is where both are true, which means this is where it would operate, okay? And we can get some intuition from that. If you were to increase Vs, what's going to happen? Can you imagine both of these points are going to move away? And so you would kind of move up and you'd pull more current. That makes sense. If I increase the voltage here, yeah, I should pull more current, right? So you would have increasing lines, right? This line would move up. This stays the same, right? This is just your diode curve, right? But the external line here would move up, okay? What happens if I change the resistance, right? Well, if I change the resistance, if I look at this equation, notice this point doesn't change at all, but this point does. If I change the resistance, this thing is going to rotate about this line, right? And let's say I increase the resistance. Well, if I increase the resistance here, Vs over R, okay, R is in the downstairs denominator. That means if this got bigger, it's going to go down, right? And so you can see increasing the resistance is going to rotate this down. Does that make sense? I would operate here at a lower point, less current. Yes, that should make sense, right? More resistance, less current. Okay, so hopefully there's a little, relationship, not just a little, it's a direct relationship between the math and the physics, right? And your intuition, which I'm always trying to point out is maybe the most important thing here. Okay, so let's look at a very simple example, right? And let's assume we have an LED. Okay, so our little red LED. Okay, and let's say it has a very simple IV curve. In fact, we're gonna assume that it's vertical, let's say, and there's a forward voltage of, let's say, 1.9 volts, but this is vertical. Now we know this is not the case, right? But it is pretty steep, so this is not a bad assumption, right? Okay, and let's say the forward voltage is 1.9 volts. You can read it off the spec sheet. And let's say we want to solve for R such that the current running through it is 14 milliamps or 0.014 amps, right? So here's our circuit. Let's say we have a 5-volt source, we have a resistor, we have our LED, and we want this thing to be 0.014 amps. We don't know what this resistance is. Could we use our simple load line analysis to figure it out? Well, we can do the same thing. We can do our nodal Ohm's law. ID equals 5 minus VD over R. And now this VD must be 1.9 volts, right? Because if we draw your load line, doesn't matter where that load line is, that voltage will always be constant in this very simplified case. Okay, now it's easy, right? Because I can plug in the ID here, and so I can solve for R. R is equal to 5 minus VD over ID. I can plug in these values, 1.9, 0.014, and we get 221.4 ohms. And this is actually the resistor we will use in our labs. So this 5 volts would be, for example, maybe a pin voltage coming out of one of these outputs, okay? So 5 volts, and I would drive it with a resistor of about 220 ohms to this LED, okay? All right, I hope this was a very nice, simple introduction to LEDs and how to use one that we'll use in lab. And I'll see you in the next part of this lecture.